Hey guys, here is the procedure for unlock part of VLSI lab. Well, I have skipped many beginning initial steps of CSH, CD, database, Cadence, MS Lab 614 and stuff. Yeah, virtuoso, ampersand, everything. I just directly jumped onto the editor window where we'll be creating an instance. We're gonna add components. Well, here we go. We have started adding components already. Actually, before adding components, there is like you should create your own library, your own name, a cell view, whatever the experiment name. Here we have given a CS amplifier as a name because that's what we are doing. Okay, we are selecting components. That's PMOS. Okay, we're giving the value of length. Yeah, that will be like 360. I kind of don't remember. Yeah, we're gonna mention the length and the width. Okay, the length will be, width will be 110 micro, and the length will be 360. Yeah, we're done. The component is ready for PMAS. We're gonna place it on the editor window. Yeah, there we go. We are gonna replace our first component. Wow. The next component will be the NMAS. You can always go click on instance or directly press I button on the keyboard and just type on the components you need, NMAS, PMAS, whatever. Then you're gonna change the properties of it, the length, the width. Actually, it's based on the design that you're gonna make. And here the design will be for 360 and some 2 4 micro thing. Okay, we are getting the connection. There goes the output. uh, you can always click on the wire on the top that's present in the toolbox, or you can also type W for wiring. Okay, we have just left it open for the pins. Okay, here we go. We are selecting pins, naming the pins, the direction of it, we are rotating it. You can always like choose between the input and output. And there's like one more thing to be added. What I've observed from you guys is you're actually confused a bit of whether to select a pin or a GND ground, that is, to place at the bottom. Well, it's always the pins in this window and the ground in the test schematic. So we're placing the pin at the output 2. We need it. Then the last one will be for the ground. Yes, see, I even mentioned it in red just to make sure for a reminder. It's the pin, not the ground. Okay, it's important, that's why I'm mentioning. Okay, let's not forget to connect the substrate thing for drain source. It's a lot of confusion. Come on, 3 pins. Whoever designed this MOSFET, come on, he's really ingenious. Actually, Cadence is a good software to play with. Okay, check and save. We're gonna save our circuit. Then we're gonna check the errors first before creating cell view for creating our own block diagram of CS amplifier, that is. Okay, now next step will be create. From create will be okay, from create, yes, create to cell view. From cell view, okay, everything is already mentioned. Let's press okay. Now here we go. Now we have to mention the pins, the name of the pins, whatever to be placed on the left, whatever to be placed on the right, the top, on the bottom. It's just we're designing a block or a presentation of our amplifier actually. We can actually make the amplifier look in whatever shape we want, or we can just keep it the way it is. Let's press OK. Okay, now there opens our block. You can always create a symbol as in like inverted thing, or you can just keep it the way that I'm doing right here. I should have placed the V bias thing on the left side, but I placed it down. Okay, it's okay. Thing matters. Let's check and save. We are done. Now file, new, cell view, create a cell view. We can, like, I've just given an example for invert and score test. Whatever we are doing here is a C amplifier, so I didn't mention it in the writing. Anyways, create instance, add instance, browse our my library, and I'm placing the component. I have placed it. Now it's time to make connections. Before making connection, let's get the components that have to be connected, like vSign, VDC, grounds. Well, that's what we need here. We are gonna take it from instance and log library and whatever the components that's required. We shouldn't be mentioning the properties of it. The DC voltage value, that will be 0 here for vSign. AC magnitude will be 1. The frequency will be 1K, and the amplitude will be 5 milli. Yes, we have done it. 5 millivolts. 1 kilo. K must be capital. Please note, K is to be capital. Okay, we have placed our sinusoidal generator. Now it's time for our VDC. We need two VDC that produces plus 1.8 volts and one VDC that generates minus 1.8, which will be given to the V bias. Why we are giving minus 1.8? Well, the output we will be getting is an inverted amplified waveform of the input. So that's why we are placing our next VDC. There we go. The last VDC for VDD. Okay, VDDs were much necessary to, let's make connections. Why? Oops, there's an open circle. Let's delete that. Let's press the delete button and delete that. There we go. We have deleted it. Then we have clicked on the wire thing, or you can just press W. There we go. We have connected it. Yes, the second one very carefully. I just left the connections open there for their stages to add ground in that place actually. I should have brought all the components on the window and get connected, yeah, agreed. But let's just make connection. It works fine either way. Because finally what you need is an output, precise output. Okay. Last one, yes, we're done. Now it's time for the ground pin that I was talking about. But let's just change this voltage. I almost forgot about it. Let's make it minus 1.8. There we go, minus 1.8. Yes, I'm done. It's 1.8. You can always change it there or even at the beginning stage. I think it's fine. Okay, let's type GND. Okay, GND. Let's hide this window. As I said, remember this is GND and not a pin. Don't be confused. There we go. We are placing. Oops, I had placed the ground almost at the output. Well, you won't get the output if you place the ground at the output because your entire wave will be grounded. Come on, you don't need that. Let's place a pin at the output for placing it to the out. Yes, direction will be output. V out. Let's hide it. Yes, and we are done with our test schematic. Let's check and save and check for errors. Yes, no errors. Schematic check has been completed without errors. That's cool. Now let's open launch ADL. There, observe window. Okay, license check. You have to press yes for that license thing because you need a license to execute. Next will be you will be going to setup simulator directory host, then select simulator as spectre. Okay, if it's not mentioned, else it's fine. If it's already mentioned, no problemo. Okay, let's start our analysis. Let's choose a transient analysis. The value we'll be giving here is 50 nano. We'll select a moderate. Okay, now DC analysis. Yes, component parameter. Before that, we should save DC operate point. Yes, done. Component parameters. We'll be clicking on VDC. Yes, that's good. That's done. Because they're giving the start and stop time. That will be minus 1.8. The stop time will be 1.8. Yes, 1. Oh, oops, sorry. It's minus 1.8. Minus, yes, done. Then stop will be 1.8. That's cool. Let's press OK. Then after that, what we'll be doing is mass AC analysis. In AC analysis, you'll be giving the frequency start and stop time. I'm actually have written some comments too, so that whatever, if you don't understand whatever I'm saying, yeah, we're done. Now the output to be plotted, outputs on to be plotted, select on schematic. We'll be selecting the wires from both input and output. Remember, you should select the line from input and output, because your whatever you're plotting is input versus output. X net lesson run. Okay, there we go. Running. 3 and 2 and 1. Here we go. Voila. This is our output. Let's separate that. The first window. See? Yes. There it goes. Yeah, I said you'll get the inverted output. The AC transient analysis, we have separated that too. Now what we have to do is select on tools, calculator. What calculator is made for? To calculate bandwidth, rise time, fall time, gain, blah 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 stuff. Okay, not the gain. Gain we will be getting it from the graph. Now what you do is you select on special function, bandwidth here for example, signal, remove whatever that's extra. Now select on the line obtained. Oh, pardon me. Okay, the table gives you, yeah, that table that gives you the output. I mean the action, whatever's going on from one frequency to another. Let's click on apply. Okay, there we go. Okay, now run. Yeah, there we got the bandwidth. The bandwidth value differs from one system to another system, because the component selections that we would be making varies from one system to another system. Although it's a software command, there's no need for precision. It's not based on theoretical value, it's always practical one. Here we're calculating the rise time. Yes, we'll be clicking on the rise time, apply. Okay, now the run. Yes, we got it. We can also calculate the fall time in the same way. I'm actually thinking, is the rise time fall time needed for CS amplifier? If yes, then cool. If no, sorry, I added it to it. There's actually a DC part left too. I have to record for that. Anyways, where was I? The gain. I tried searching the gain in the special function. Then I realized the gain to be plotted, or the gain to be obtained, is from the graph itself and not from anywhere else. From the graph. Again, from the AC response graph. There you see the DC response. Yeah. Smooth curve. It's, uh, it's actually very cool to work with Cadence. The software is awesome, whoever designed it. Let's close everything. Yeah, let's save the output that we have got, because we need this plot in next stage, the coming stage in layout. Now it's time for the layout. We are done with 50% of thing. Now let's start with the layout. There we go. Launch. From launch we'll be taking out layout Excel. Okay, now create new automatic. Okay, layout thing is selected, library name. Okay, there we go. Here is our layout window. Now what is this layout thing? See, whatever the component that you have connected, layout is actually whatever that's inside the component. The polysilicon, the metal connections. You would have studied that in CMAS, and I don't have to mention it to you. Now, here you have to take that, go to input output selection because you need the labels, right? We'll be moving the entire component towards the fourth quadrant, towards left. Press shift F. Okay, here it is. If you press shift F, you'll be like getting this colory thing. I had pressed control F by mistake, so I got some window. We'll be like removing that blue thing. That's not needed actually, and that was an extra line. Okay, now we will be rotating our components the way we want to make it look neat and cool. Well, that's what we want, right? The appearance should be cool and the performance should be neat for any system. Let's select our components and rotate it. You can always right click on it and click on rotate and rotate left or rotate right. Rotate left or rotate right, that's all. No horizontal or vertical flips. You just place the NMOS below. See, you can observe this. The lengthy one will be the PMOS. The shorter one is the NMOS. Make sure while placing the NMOS, the length from the PMOS or the envelope that you will be drawing around the PMOS in a while, the length should be lesser than 10 micrometers. I repeat, lesser than 10 micrometer, not more. And you can always select on metal and press R for to draw a rectangular connection. And here it is another thing to be noted here. The width of the metal that you're drawing must be greater than 0.3 micrometers, not lesser than 0.3 micrometers, or you would be dealing with some errors. And come on, you don't want to spend your externals, that precious external time in correcting your errors, right? So that's what. Now let's draw the anvil. Yeah, there we go. We have selected on anvil and we have drawn a rectangle. You can select on the anvil and move it up and down, or you can just press S on the keyboard and just stretch the anvil the way you want. Here's the mistake that most of us, not of most of you actually, not me, do is we draw an unnecessary metal line from the anvil and we try to take it out from that and put a VDD. Come on, VDD is to be placed inside. Okay, I'll be skipping few steps here and I will be going directly to the complete finished and saved layout instead of just showing you the connection and wasting some more of the time. And yeah, another point to be noted, I have seen some people draw an unnecessary line from the output too, which is not necessary. You can always place the VDD directly into the metal line. Yeah, there we go. That line that's actually not needed. I'm actually showing you the what the popular mistakes that students do while drawing the schematic, sorry, drawing layout, pardon me. Okay, let's delete that extra stuff too, it's not needed. And here another mistake, this is one more, the third one. They tend to draw a metal connection from a polysilicon. Come on, you don't need an open wire coming from out from a circuit, right? A wire will be having a jacket covered insulating material. The same way, you need a polysilicon that's gonna come out from there. You can always click on Control Shift W for getting a precise wire of greater than 0.3 micrometer, or you can draw a rectangle as I've shown here. Make sure the width matches, because the width of the polysilicon in the NMOS is exactly 0.3 micron. It should be like equal to or greater than Press stretch. For stretching, press S and stretch. If the wire is already selected, deselect it and stretch it. Okay, what I have shown here is the completed one, the VDD connection. Okay, the polysilicon to metal wire that is placed here. Okay, that's done. There the line you can see on the right side is scale, the VSS wire where I have given the substrate to metal. Yes, that's the difference. Okay, we are done with our connections. Now let's run DRC and check for errors. I'm running this once again. I have already completed all the stage. I'm just doing it once again just for you to know it. Okay, let's press yes. Okay, done. We'll be checking for errors. No DRC errors. Now that's what we are expecting for. Even if you get some errors, what you'll be doing is checking the errors and just like you'll be removing all this. Now this is a LVS window. Yes, let's check it. Yes, okay. We'll be waiting for our LVS to run. Now what is this LVS? LVS is nothing but a layout versus schematic. Now, okay, we're waiting for the window to appear. As I said, Cadence is a good software to actually play with, and we are not much exposed to this software. So, okay, here it is. No, not this one. I think it should be appearing on the right side. Come on, yeah, we got it. Zero errors. Now, what here we will be having in LVS is the LVS compares the schematic and the layout and gives out whatever there's that mismatch. Okay, let's run the QRC. Let's not go in detail. Let's set the output to the extract view. The fourth thing you will be seeing there. Okay, the parasitic, you need not include any resistor or capacitor value that's gonna be appearing unnecessarily, because whatever you will be needing is just an output waveform, the gain, whatever that is, because only then you'll be completing your experiment successfully in both layout and schematic. Okay, setup. There you can see the output will be in spice, extract mask diffusion district, no other changes to be made. Net listing, we're going back to the net listing just in case we need to check if there's any modification that's needed. Okay, there in output you just select that to extracted view, then you mark it there, extract mask diffusion. After clicking that, I'm just cross checking it again. You're just clicking the diagonal thing, then you don't need to press apply, you just press OK. When you click on OK, appears okay. Yes, you're just overwriting it. As I said, we have already finished this. I'm doing it once again just to show you how it's done. Okay, we'll be waiting for the QRC dialog box. Come on. No, not this one. Okay, it will be towards the right side. Okay, the QRC window, where is it? Where is it? Where is it? Come on, come on. Where are you? Okay, yeah, we got it. QRC run dialog box. It says AV extracted. If you want, you can see it once again. I want AV extracted. Now you have to close that. We don't need that window actually, so I'm gonna close that. We are done with the 75% of the experiment. Just 25 more to go. Now what we have to do is we have to go to the library and we have to like create a new thing. Okay, I was actually searching for it because I need this configuration window for simulation. That's very much necessary because this configuration is a post layout, is for post layout simulation. There we go. Library manager, file, new cell view. Oh, sorry, this is someone's else. This is not mine. Come on. We are actually searching for a CS amplifier that I that we just rigged up. Okay, we'll do it once again. New cell view. uh, there will be some box appearing there, dialog, where you can actually modify whatever that is. New. Oh, it's minimized actually. Let me open that directly. Yeah. Yes, done. Type config hierarchy editor. That's done. Now let's press OK. Now our new configuration. I will show you it once again. Show this once again. File, new, cell view, then type configuration. Okay. Then a new configuration will open where you will click on, will view schematic, then you click on use template, then the name will be spectre, then apply. Okay, yes, you're done. Now okay, yes, we'll get this tree view thing. Right click on the file, then go to the set instance view. From there you get that AV extracted. Select on AV extracted, save and close this. We are done with the 80%. Now all we need to do is double click on configuration and press OK. Okay, we are done, almost done. Let's save this, yeah, and close. Yeah, I'm a bit slow in doing stuff, but yeah, okay, now it's time for the configuration. Let's double click on the config right there in the third column. Yeah, double click. Yes, there will be some dialog box appearing there. Then you click OK on that. As soon as you click OK, you'll be getting the test schematic, the whatever that you had done before. Okay, I'll show you to you once again what we have done and how we have done. Let's close this and go back to the same window where we double click that configuration thing. We're just 2 minutes away from the output. There we go. We will be closing this. Okay, the launch ADL session load set will be for the next one. Let's double click on the config. I'm showing it to you once again. Okay, press OK. The test schematic will be appearing there. You'll be clicking on launch ADL session load state. Okay, if you went, there's no changes needed here in this loading state ADL. As soon as you press OK, you will be getting the same thing, yeah, that you had given in the test schematic, the input output plottings. Well, you will be running the same thing. I'll be showing you it once again. Launch ADL, then go to session load state, then OK. You'll be getting the states. Good. Now outputs to be plotted. Oh, it's already present there, but I'm showing you just in case if it's not loaded. You can always go on, select on layout, the schematic, but since it's already here, we'll be just doing is run. Okay, there it goes. 3, 2, 1. Voila! Ta-da! Here it is. Well, we got the output. Come on. I need some whistles and applause. Thank you. Thank you for all your time. Thank you for watching. Hey guys, here is the procedure for like part of